Welcome, we're Group 7 from Section 1, and this is our lab practice called Thermal Conductivity in Composite Materials. We've divided our lab practice in several sections, which are Introduction, Proposed Methodology, Lab Methodology Results Analysis, and finally our conclusions. But what are composite materials? Well, these are the combination of two or more materials that result in better properties than when the individual components are used alone. And they are composed of cohesion or matrix and the reinforcement components. For this lab practice, we use PLA, which is a thermoplastic polymer made from lactic acid, which replaces traditional polymers thanks to its biodegradable properties. And it can be used as a matrix material in composite materials. It has great properties such as its high mechanical strength, that it's biodegradable, it has good barrier properties, it's recyclable, but it also has some inconvenience, which are its poor thermal stability and its low impact resistance. What will be analyzed in this lab is the thermal conductivity, which is the ability of a material to transfer or conduct heat. Electrons and phonons are energy carriers, and electrons are for metallic materials, and they transport thermal energy as they move through the structure of atoms. In nonmetallic materials such as insulators and semiconductors, heat is transported by phonons, which are quantized by vibrational modes of atoms in the crystal lattice. The probability of the direction of the heat transferred is 1/16 for three-dimensional crystal lattice. It is important to clarify also that for anisotropic materials, the thermal conductivity varies with the direction. In order to calculate the conductivity of different materials in this lab practice, the Fourier's law was used, which is the one shown in this presentation. With the information mentioned before, our goal with this lab practice is to determine how the composition affects the conductivity of composite materials. In order to achieve our goal, our group proposed the following methodology. We proposed the differential scanning calorimetry, DSC, and to do so, first it had to be turned on and calibrated, then the samples must be weighted and they have to be put in a crucible press with a lid. Then the samples are inserted in this DSC. Then the temperature limits and steps as function of a time are set. And then we have two options, which are to obtain the data for heat flow and then calculate the thermal conductivity with Fourier's law, or to obtain the data of the conductivity by the DSC. This is how the DSC looks. Now the methodology used in the lab will be shown. For this practice, we have four different filaments, which are PLA with rice husk, polypropylene with cocoa, PLA with graphite, and finally copper. First, the filaments were cut to a length of 9 centimeters to have them all to the same size. Then they were marked in three sections of 3 centimeters, and the heating plate was preheated to 120 Celsius. Then the filaments were glued using tape to the plate, and 30 seconds were determined to take the measurements. And finally, we took the temperature of each filament every 30 seconds at each section.
Now we are going to present the results. First of all, for the PLA and graphite filament, we made three graphs that correspond to the change of the temperature with time for each region. First, the one from 3 centimeters, then 6 centimeters, and finally 9 centimeters away from the heat source. From the measured temperatures, a linear fit was carried out in order to obtain the derivative of temperature in time for each region. As we can see, the slope of the line is positive, meaning the temperature increases in time. However, as we move on away from the heat source, the slope of the graph decreases. On the other hand, a graph of temperature as a function of distance was made, and it can be seen from the data obtained that there is a decrease in temperature as we move away from the heat source. This behavior was described with a second-degree polynomial whose second derivative was calculated in order to determine the conductivity of the filament. On this occasion, a single graph was made to simplify the calculations. In the case of the PLA and rice husk filament, the same three graphs of temperature as a function of time were made. When performing the linear fit, the same behavior seen previously was obtained, in which the positive slope decreases as the distance of the heat source increases. However, a greater temperature change in time was evident compared to the PLA and graphite filament. As before, a graph of temperature as a function of distance was made for this filament, and it can be seen from the data obtained that the decrease in temperature continues as we move on away from the heat source. By describing this behavior with the second-degree polynomial, a second derivative of the temperature with the distance was obtained, and this one was smaller than the one of the PLA and the graphite filament. With the polypropylene and cocoa filament, the temperature versus time graphs presented a decrease in their slopes compared to the filaments mentioned previously. Regarding the second derivative of the temperature in terms of the distance for the polypropylene and cocoa filament, it is superior to those of the previous filaments. Finally, we have the results for the copper filament, where you can see how in the linear fit the slope increased slightly compared to the polypropylene and cocoa filament and the PLA and graphite filament. Also, as we move away from the source, the slope decreases. In the graph of temperature against distance, we can see the same behavior seen for the other filaments. Therefore, by adjusting to a second-degree polynomial, the second derivative of the temperature in terms of distance was obtained. With all the results shown above, the conductivity was calculated for each one of the regions of each filament studied.
Now we will move on into the analysis. Through the graphs, it is possible to observe the behavior of temperature through time. While the filament was positioned touching the heat plate, in each of the regions through time there is an increase in temperature. In terms of each filament, it is possible to observe how in the first region there is a bigger conductivity. This is because the transportation of heat typically behaves from colder to hotter. In this case, the first region was close to the plate and therefore in the last region there will be less heat reaching it. This is the same behavior for each filament. The region that has the biggest conductivity is the first region. This one was positioned in the first 3 centimeters. Another reason for this is that molecularly, heat conductivity is deeply related to the collision of molecules and their intermolecular distance. This was explained with the lattice size model. While there is a bigger intermolecular distance, there will be less heat transfer. Because the first region is receiving the heat directly, the energy will increase. There will be more collisions and therefore less intermolecular distance between the molecules, and there will be more heat transfer. Now, observing the graphs related to distance versus temperature, it is possible to understand that the composite materials that are being worked with are anisotropic. This is mainly shown through the jumps that are done throughout the filament. The representation of those jumps are the dots on the graph. They represent when the temperature makes a drastic change when the longitude increases. All the jumps happen in the 3 centimeter mark. Relating this to the data, it is possible to see how in each measured length there is a different heat transfer. This confirms the anisotropic behavior of the materials. The fact that they are anisotropic explains that they have different properties in the direction that is being analyzed. After the different graphs were analyzed, it was possible to obtain an experimental value of the thermal conductivity of the different composite materials. These results also describe and confirm the fact that the materials are anisotropic. This is because in each of the different regions the conductivity varies. It is also shown how the closer the region is to the heat plate, the bigger the conductivity is. Now, in terms of the values, it is seen how the filament of cocoa and polypropylene have the smallest conductivity. Then it comes the PLA and rice husk filament. Then the PLA and graphite filament, and finally the copper filament that resulted in the biggest conductivity. In terms of the best conductor, it is seen that the copper filament was the best. This is because the free electrons in metals are good in the moment of transferring energy. When heat is applied, they will vibrate and collision, and in result, heat will be transferred. Additionally, metals consist of crystal lattices. These are arranged very neatly, and in result, this allows the photons to propagate through the material. A photon is an excited state of vibrations in a crystal lattice. For this same reason, graphite is also such a good conductor. Graphite also has a crystalline structure and has a dislocated electron. This will result in movement and conductiveness. Because it was mixed with polylactic acid, the conductivity will decrease. In comparison to the filaments containing cocoa and rice husk, this can be shown to have low conductivity. Because in these materials, their structures have relatively big intermolecular spaces between their layers, this causes for less collisions to happen and in result less conductivity. For other applications, for example for an ice cream shop, it is necessary to use an insulating material. This could be ceramic or glass. And for example, in a heat exchanger to increase the temperature of different components, it will be interesting to use stone.
When the methodology proposed by our group and the one made in the lab are compared, we can find that there's a greater error in the results with the lab methodology because there were some complications taking the temperature every 30 seconds and trying to stay still using the thermometer. On the other hand, the DSC only has from 10 to 20% of error, and this is why the results are closer to literature than the ones we obtained in the lab. In both methodologies, the Fourier law can be used, and it is needed less equipment for our lab practice because it only needed a heating plate, whereas in the DSE, we needed the DSE.
Finally, we will move on into the conclusions. In conclusion, throughout the practice, it was seen through the resulting graphs how heat conductivity is deeply related to the collision of molecules and their intermolecular distance. While heat is increased, collisions between molecules will happen, and their intermolecular distances will reduce. It was demonstrated how the composite materials used were anisotropic. This means that their conductivity will not behave the same way in their direction that is being analyzed. Finally, it was described how the best conductors were related to the copper and graphite filaments, and the insulating ones were the cocoa and rice husk filaments. Finally, here are the references used. Thank you very much.